Hey there! In this video we are looking at applications of logarithms in real-world situations. Specifically, we're going to look at what are called log scales, which is something that you can use when you're comparing values that have vastly different magnitudes. Now, before we look at any specific real-world applications of this, we're going to look at it a little bit in general first. Now, logarithmic scales or log scales are a way of showing data or values using powers of a base number, and that's of course usually 10 in our number system. And what it does is it allows you to show data or values that have a really wide range to them or vastly different magnitudes. Now, certainly what you're used to is a traditional linear scale, although you've likely never called it that. That would be something like a ruler or a tape measure or the scale on a graph when you're graphing, where each step on the scale represents the same increment, the same distance, the same amount. Whereas a logarithmic scale, each step on that scale represents multiplying the previous step by that base power. So what happens is distances on that scale don't represent the same increment. The values on the scale are the logarithms of the actual values. Now, we're going to use a simple made-up example to kind of see how this works. And that simple example is one where you have people with different amounts of money. So we have three people here, Alex, Blake, and Casey, and they have $10, $20, and $30 respectively. Now, we're going to put them on this linear scale. So again, linear scale, just like a ruler, right? And what I mean by that again is every space here represents the same distance. Every space there is 2 on this scale. All distances are the same. Now, if we're going to put these people on there, of course, we have Alex, who's going to be right there at 10. We have Blake, who's going to be right there at 20. And we have Casey, who's going to be right there at 30. That scale works fine to show those values. All three of those values, all are 2-digit numbers. They're all in the same magnitude, the same ballpark, really. What happens if we add someone else here? So if we add a fourth person named Drew, who has $100, well, we certainly can't represent them on that scale. But if we create another one here where it goes up high enough, then of course Drew is right there at 100, and we can still represent these other three, Alex, Blake, and Casey, on there. All right? What if we add a fifth person named Ellis who has $1,000? Well, we need a new scale here that goes up high enough, so it's going to look like that, 1,000 up there where Ellis is. And representing the others, well, if that's 1,000, then each step on the scale here is 100, and that is where Drew is. And then the other three are going to be, if this is 50 here, well, they're all going to be down there near the beginning of that scale. And now if we continue this and we add one more person to this, if we add Francis, who has $1 million, and we want to show this person on the same scale. Well, the scale has to go up high enough there. It has to have 1 million at least at the top, and that's where Francis is. And now if that's 1 million, then each of these spaces is 100,000. If this is 100,000 and we want to show 1,000 where Ellis is, this is 100,000. Well, it's 1/100th of that. Right? So it's going to be down here somewhere. And that's actually where all of the others are. If you try to locate the other 5 on this scale, they'll all appear right there. You won't be able to tell the difference between those 5 of them, even though they have vastly different amounts of money when you compare them just to each other. So this is an important thing to recognize here when you're looking at this. And this is really the reason why people use logarithmic scales is as the range in the values increases, then the smaller values get all compressed together and it's hard to see the difference. All right? Now, we're going to put them on a logarithmic scale, and you can see how that works. So to put them on a logarithmic scale, we need to put their logarithm on a scale. If we think about the logarithms of these numbers, well, let's look at the logarithm of the top one here. The logarithm of 1 million, that's 10 to the power of 6. So we're going to represent that with a 6. That's the highest we need to go. So our scale can look like that. Now we're going to put those numbers 1 to 6 on there, but really it's important to remember that they actually represent 10 to the power of those numbers. So Francis is going to be right there at 6 because it's 10 to the 6th that they have. And then the other people, Ellis, who has $1,000, 1,000 is 10 to the 3, the logarithm's 3, so we're going to put them right there. Drew has $100, 10 to the 2, so we're going to put them there at 2 on the scale. And then we can put the others as well. We just need to know what their logarithms are. We can put Alex there because $10, 10 to the 1 is going to be right here. And then the others are going to be in between there. We just need to know their logarithms. First, if you go to a calculator, you'll find that the logarithm of 20 is about 1.30, and the logarithm of 30 is about 1.48. So if you put them roughly on there, that's where Blake is, and that's where Casey is. All right? So you can show them all on here on the scale. You can use a number to represent them that is fairly easy to compare to each other. The important thing to recognize, though, is each of these jumps represents multiplying by 10, not adding some amount. If you think about it, that distance in there from 10 to 100, that's 90, right? This distance is 10. This distance is 100, right? It's not twice as much. It's 10 times as much. This distance is 1,000. It's 10 times as much again. Distances on here don't represent the same thing, all right? Now, one last thing here before we move on to looking at some real-world examples of log scales. We're going to look at this situation in a more dynamic way. Now, that's a scale similar to the first one we used, where we could show Alex and Blake and Casey on there. But then to show Drew, we had to compress this down a bit so that we go up to 100. And then we could show Drew on there. But then if we wanted to show Ellis on there, we had to compress this down again, so we get it to go up to 1,000, like that. And Ellis can be on there. Now these three here are already pretty close together, but you can still see that they're different. If we want to show Francis on there, we're going to really have to compress it. Now those are already together there quite a bit, and we're only at, this is only up to about 160,000. It's hard to even tell the difference there. If I want to go up to 1 million here, I have to go to about there. There's 1 million on the edge right there so that you can show Francis. The rest are all clumped together there, as we saw earlier. That's the real reason people use logarithmic scales. Let's move on and look at some real-world specific examples. Probably the most well-known example of a logarithmic scale is the Richter scale. It was developed by an American seismologist named Charles Richter, and it is used to express the magnitude of earthquakes. Now, it's a logarithmic scale, and it's exactly the same as the scale we just looked at with the money and those people. A difference of 1 unit on the scale represents a factor of 10 difference in intensity of earthquake. So if you have a magnitude 4 earthquake, it's 10 times as intense as a magnitude 3 earthquake, or 100 times as intense as a magnitude 2 earthquake. All right? Now, the first part here asks us, how many times stronger is a magnitude 7 earthquake than a magnitude 3 earthquake? Well, if you want to express this, how many times stronger, we often think of it as the ratio of intensity. And so we're not doing the ratio of these numbers. We're not saying 7 divided by 3. We are looking at 10 to the 7th divided by 10 to the 3. This is the place on the scale, but the actual number representing how intense the earthquake is 10 to the 7 and 10 to the 3. And we can write that instead as 10 to the 7 minus 3, of course, using exponent rules. And then, of course, you can simplify that to 10 to the 4th, which is, of course, 10,000. It's 10,000 times stronger. Magnitude 7 is 10,000 times stronger than a magnitude 3 earthquake. All right? Let's look at another earthquake example. Now, here we're going to compare a couple of earthquakes that happened pretty recently to when I'm uploading this video. One of which you likely heard about in the news. It was a magnitude 7.7 earthquake that happened in the country of Myanmar. And the reason you heard about it is because it was unfortunately really devastating and destructive, and there was a lot of death and damage that occurred from that. Now, just over a month earlier, there was a much more minor earthquake that occurred really near where I live here in Vancouver, BC. It was a magnitude 4.7 earthquake. And I was at school. My students and I were kind of looking around thinking, did we feel something? Yeah, I think we just felt something. So the reason I bring that up is because when you just look at these numbers, 4.7 and 7.7, I think people forget that those are on a logarithmic scale and think maybe 7.7, 4.7. Well, 4.7 is more than half of 7.7, so they sort of subconsciously compare them that way in their mind, but that's not how you compare those numbers. On a logarithmic scale, of course, if you're looking for the ratio, like we're looking for how much stronger was the Myanmar earthquake than the one near Vancouver, we're essentially looking for the ratio of how intense each earthquake was. And so we could write it as a ratio, as a fraction, or as we saw in the previous example, we can go right to writing it as a power of 10 with those exponents subtracted, and that is 10 to the third. Really, all you need to do is just look at the difference in the magnitudes, and it's that power of 10. 10 to the third. There's 3 different between 7.7 and 4.7, so it's 10 to the third. That's why people use this scale, because it's really easy to quickly come up with the ratio often. And so 10 to the third is 1,000 times stronger. Last earthquake one we're going to look at, the largest earthquake ever recorded was called the 1960 Great Chilean Earthquake. It was a magnitude 9.5 earthquake. And we're going to look at here, how much stronger was that than the one that I just said was pretty devastating in Myanmar? Again, we can write that the ratio is the same as that power of 10, 10 to the 9.5 minus 7.7, which is, of course, when you subtract it, 10 to the 1.8. This still works when this is not a whole number. The first couple were whole numbers, but that's not a whole number. That's fine. You just need a calculator to work that out. If you go to your calculator and work that out, you get that it's 63 and change, so approximately 63 times stronger. This is less than 2, so it's less than 100 times stronger, but it's bigger than 1, so it's more than 10 times stronger. Remember that the difference of 1 in magnitudes represents 10 times. A difference of 2 represents 100 times. So you can kind of estimate sometimes that way too. And actually, that wasn't the last part we're going to look at. We're going to look at one more part here. So here we're thinking about kind of working in reverse here. Here we have a major earthquake of magnitude 8, but we're saying it's 6,500 times stronger than a smaller earthquake. How can you find the magnitude of the smaller earthquake? Well, what I'm going to do here is I'm going to use a variable to represent the magnitude of that smaller earthquake. And I say again, it's smaller, so let's recognize that x will be lower than 8. Just in case you set it up wrong, you need to know what you're looking for. So we can kind of use a similar setup that we had there. The ratio is those two things divided, except for now we don't know one of them. What we do know is we know this ratio. We can substitute 6,500 in for that. We know it's 6,500 times stronger. We can put that in there, and then we can even write this as our power of 10 using the exponent law for division. Once we have that, it's just going about solving for that variable right there. So we can take the logarithm of both sides of that, and then we can proceed to solve it. Once we take the logarithm of both sides, and then we can cancel that out. And so on the right side, all we have is 8 minus x. And on the left, we have log of 6,500. I think the best way to isolate this is to move the x to the left side and then move that log 6,500 to the right side. So what you have is x equals 8 minus log of 6,500. And then if you go to your calculator and work that out, you're going to find that it's about 4.187, or in other words, we can say that our magnitude is approximately 4.2. If we round it to one decimal place, which is usually what you do with values on the Richter scale. If you were working with the Richter scale all the time, you'd probably get to the point where you'd have it simplified in your mind to thinking, if I have a magnitude 8 earthquake and then I have a smaller earthquake that's 6,500 times less intense, I just subtract log 6,500. if you added log 6500 here, if this was plus, you'd end up with something that is 6500 times more intense. If you take the logarithm of the ratio of intensity, that's how you can add or subtract on the Richter scale. All right, let's look at a second example of a logarithmic scale. Another really well-known example of a logarithmic scale is that for the loudness of sound, which we often just call the decibel scale. Now, the intensity or loudness of sound was originally measured in bells, which are named after Alexander Graham Bell, the inventor of the telephone. But the current unit that's usually used is the decibel, which is equal to 1/10 of a bell. And the Bell scale, just like the Richter scale, is logarithmic. So a difference of 1 bell, or 10 decibels, corresponds to a factor of 10 difference. So in our first situation here, if we have the sound of normal conversation, which is 60 decibels, and whispering, which is 30 decibels, you look at that and you might say, oh, 30, 60, 60 is twice as much as 30, so does that mean it's twice as loud? It's not that simple, of course, as you've seen already with the Richter scale. What we have to do, first of all, this has the added wrinkle of the scale is in bells, not decibels. So you're usually given sounds in decibels, but the scale is in bells. So we have to think of this as 6 bells, and we have to think of this as 3 bells, and compare them that way. So again, the scale is logarithmic in bells, not decibels. So when we're working out the ratio here of how intense those two sounds are, we can write a ratio just like we did as a fraction, a ratio of powers like that. It's just that these have to be in bells, 6 and 3, not 60 and 30. That's the important thing to remember here. And then, of course, you could write that one as 10 to the 6th minus 10 to the 3, which is the same as 10 to the 3, or, of course, 1,000. And so that is 1,000 times as loud. A normal conversation is 1,000 times as loud as whispering. All right? Our second part here, they say that the sound that a motorcycle generates for the rider can reach 116 decibels when you're driving at highway speed, whereas the typical car, when it's driving, might generate a sound that is 73 decibels. How much louder is the motorcycle than the car? Again, we can do the same thing here. We can write our ratio of the intensities, but we have to remember that 116 decibels is 11.6 bells, and 73 decibels is 7.3 bells. And when we write this ratio, or I'm going to write it as a power with those exponents subtracted, 11.6 minus 7.3. Again, that wrinkle with the decibel scale, you got to convert it when you're comparing. And so that's equivalent to 10 to the 4.3 when you subtract it. Again, it doesn't have to be a whole number difference. And 10 to the 4.3, if you go to a calculator, you're going to find that that is roughly 19,952.6. So let's round it to the nearest whole number and say it's approximately 19,953 times as loud. That's a lot louder. Third part here, we have two people each playing the trumpet, playing together, and each trumpet has a sound with a loudness of 80 decibels. How loud is their combined sound? And I find even if people feel like they understand these logarithmic scales, then they get tripped up when they see something different, maybe like this, because their go-to immediate right away answer is to say, oh, 80 decibels, there's two of them, must be 160 decibels. Well, that's not how it works with a logarithmic scale, and you'll see why here as we go through this. So you have to think about this here. The total sound is going to be the sound of trumpet number 1 added with the sound of trumpet number 2, right? You're adding those two trumpets together. And just like before, we need to say that each of those is 10 to the 8th because 80 decibels is 8 bells. So you have 10 to the 8th and 10 to the 8th. What that is together, their combined sound, the actual value is 2 times 10 to the 8th. And if you want to find where that is on the scale, if you know the actual number, you just take the logarithm to find where it is on the scale. Just like we did at the beginning with the money example. We took the logarithm of the number to place it on the scale. So the sound level is going to be the logarithm of 2 times 10 to the 8th, which is 200 million, basically, log of 200 million. You go to your calculator, that is going to give you 8.3. Remember that that's bells, so you can say that it's 83 decibels. Now again, to reiterate here, it's the sound intensities that are added, not their decibel or bell values. So it's definitely not 160 decibels, but as I said, that's the really common kind of incorrect answer for this. That would be if you had 200 million trumpets each creating that sound. That would be 160 decibels. All right? Let's look at one last application that involves a logarithmic scale. Now, another really well-known example of a logarithmic scale is the pH scale in chemistry, which is used to express how acidic or basic solutions and other substances are. Now, the term pH was introduced over 100 years ago, 1909, by a Danish chemist named Søren Sørensen. And he chose that term because he wanted a shorthand for the power of hydrogen, because differences in concentration of hydrogen ions in solutions is what makes them more or less acidic, and there's a really wide range of possible values, so a logarithmic scale is really useful in this situation. Now, this logarithmic scale is the same as any of the other ones that we've used before, where a difference of 1 unit of pH corresponds to a factor of 10 in acidity or basicity, more or less. Now, there are a couple of differences with this scale that I've actually already kind of alluded to. There's sort of two directions to this scale. One direction on the scale, you say things are more acidic, and the other direction on the scale is the opposite of that. You say they're more basic. So this scale, the numbers range usually from 0 to 14, but the value of 7 in the middle represents neutral, something that is not acidic or basic. Values of pH that are below 7 represent things that are acidic. There are more hydrogen ions, and values of pH that are above 7 represent basicity, as in there are fewer hydrogen ions. The lower the pH value, the more acidic something is. The higher the pH value, the more basic it is. All right? In our first part, we're looking at here, how many times as acidic is Pepsi, which has a pH of 2.5, as compared to typical tap water, which has a pH of 7.5. Now, if we want to compare these things, we do exactly the same thing as we did for our other two logarithmic scales. But the thing we have to recognize at the start here is if we're asking how many times as acidic is it, we have to remember that lower pH is more acidic. So when we write an expression to represent the ratio, either as a ratio or as a difference of powers like that, as a power of 10, we want to do 7.5 minus 2.5, which is, of course, 10 to the 5, or 100,000. And so even though this is a lower pH than this, we're going to say that it is 100,000 times as acidic. Pepsi is 100,000 times as acidic as typical tap water. Typical tap water is actually slightly basic. It's above 7 at 7.5, and Pepsi has this fairly low pH of 2.5. So 100,000 times as acidic, or the other way you could actually say that is you could say that it is 1/100,000th times as basic as typical tap water. That would be an uncommon way to say it. Usually you'd say Pepsi is 100,000 times more acidic than typical tap water, or you'd say typical tap water is 100,000 times more basic than Pepsi, right? And that's just because the difference on the scale is 5 between 7.5 and 2.5. Let's look at one other part here. Here we're going to compare rain. Typical unpolluted rain is actually slightly acidic and it has a pH of around 5.6 on average, and that's because it has some carbon dioxide dissolved in it, which makes it slightly acidic, whereas seawater is around 8.1, and it's actually slightly basic, and that's because it has salt in it. And so we're looking at how much more basic is seawater than rain. We can write a similar expression. And again, the first thing to recognize here that if we're asking how much more basic something is, higher pH is more basic. And when we write our ratio, we write it as this power expression again. I'm still going to put the bigger number first, 8.1 minus 5.6, and that's going to give me 10 to the 2.5. Go to the calculator. You're going to get approximately 316.2. And so you can say that seawater is approximately 316 times as basic as typical rain. All right, our last part here to do with pH. We're looking at something that's really acidic, which is stomach acid. Has a pH of about 1.5. And we're going to compare that with something you might put in your stomach, which in this situation is a particular unnamed coconut water beverage, which is 50,000 times less acidic than stomach acid. And so we're looking for what's the pH of the beverage. And this is similar to a part of an earlier example that we did where we're looking for the unknown value on the scale, but we know the ratio, how many times more or less it is. And we could do something similar to what we did then, which was use a variable to represent the unknown pH of the beverage. And we have to remember here, again, the two directions on the scale. The beverage is less acidic, so the pH is going to be higher on the scale. And so if we write our equation here, well, we can write that 10 to the x minus 1.5. The pH of the beverage is higher, so I'm going to put it here, right? It's bigger, which is equal to the ratio of 50,000. If we go about solving that, again, we can take the logarithm of both sides. After we do that, of course, this cancels out. And on the left, we just have x minus 1.5. And on the right, we have log of 50,000. To solve that, I think the best thing to do here is move that to the other side. And so you have just an x on this side, and then you have 1.5 plus log of 50,000 on the other side. If you go to your calculator, you're going to find that that is roughly 6.19897, or we can say roughly that is pH of 6.2 for that beverage. Now, as I said in a previous example, if you were working with this all the time, you'd really simplify this in your mind so that you're thinking, if I have a pH of 1.5 and I want something that is 50,000 times less acidic, as in I want to move up the scale by 50,000 times as much, I would just figure out what log of 50,000 is and add it on. It's going to be that much higher. All right, that's it for logarithmic scales. Hopefully with those 3 real-world examples and our one made-up one at the beginning, you understand how they work and can work with them.